Hello everybody. Welcome to the lecture series Foundation for VLSI Design. This is the sixth lecture. In this lecture, we'll be discussing semiconductor physics. Specifically, in this lecture, we'll be looking into semiconductors, then we'll be looking into carrier transport, and then finally we'll be looking a bit on PN junction. First, let us look into what is a semiconductor. So semiconductor is a material which has properties, or especially the conductivity, which is something between a conductor or good conductor such as metal and a bad conductor or insulator such as say wood, rubber or silicon dioxide, right? So what are examples of semiconductors? So the most common elemental semiconductors is silicon and germanium, right? So the silicon is most widely used in the semiconductor industry, right? And there are many compound semiconductor, meaning that these semiconductor materials are obtained by combining various elements. For example, gallium arsenide, indium phosphide. These are semiconductors which are examples of what we say as group 3,5 semiconductors. Why? The first, because these in this material, for example, gallium arsenide, the first one is of group 3 in the periodic table, and the second, that is arsenic, is group 5 in the periodic table, right? So these are compound semiconductors which are known as group 3,5 semiconductors. And there are many other semiconductors materials which are used and are in research for for application in integrated circuits. Now, we said that semiconductor material has conductivity something between good conductor, and insulator, right? Now, in a semiconductor, how does the current flow, or what types of are the carriers for current flow, right? So, in semiconductors, there are two types of carriers, right? Though the first one is the electrons, which are created by breaking of covalent bonds, right? And by breaking the covalent bonds, the electrons become free to move, right? So let us understand with the help of a figure, right? So this is a representation of a crystal lattice of say silicon, right? So silicon has a valence, four electrons in its valence band, and those will be bonded by covalent bond in the semiconductor crystal using these covalent bonds, right? Now, because of various reasons, for example, elevation of temperature and the some electron which are in the valence band, some electrons which are in the valence band, they can acquire sufficient energy and they can go to the conduction band, right? The electrons go from the valence band to the conduction band, right? Or we can think of it that one of the covalent bonds get broken, right? And electrons become free to move, right? So these electrons will be responsible for conducting the current or carry current transport in a semiconductor. But when the electron moves from say valence band to the conduction band, then another thing happens. What is that another thing? The other thing is that there is a vacancy created in the valence band, right? This vacancy can be easily filled by electrons which are already there in the valence band, and as such these entities which are vacancies in the valence band, these are known as holes. So holes are vacancy created in the valence band, and electrons in the valence band can fill up that vacancy in the valence band very easily, and that can be responsible for the current transport. So in a semiconductor, there are two types of carriers, electrons and holes. So electrons are negatively charged and holes are considered as positively charged because it is a kind of absence of negative charge, which is equivalently a positive charge. So in a semiconductor, we can also have free electrons in the conduction band and free holes in the valence band by doping the semiconductor. By doping, we mean that we add another kind species into the semiconductor crystal, and as such, extra electron or hole pairs can be created. Such type of semiconductors are known as extrinsic semiconductors, right? So there are two types of extrinsic semiconductor. The first one is n-type extrinsic semiconductor, in which there are extra electrons, right? And these extra electrons are created if we dope, say, silicon with a group 5 atoms, right? So note that group 5 atoms have 5 electrons in the valence band, while silicon has 4. So there is one extra electron in the valence band in the in the group 5 atoms, which will be responsible for being having a free electron in the lattice, and that will be responsible for the current flow, right? So pictorially we can see that if there are we add say phosphorus atom which has got five electrons in the outer shell. Four of them will be bonded to the adjacent silicon atom, and one will left unbonded or will be free. So we can also look into the valence sorry the band diagram view of the extrinsic semiconductor. So in an extrinsic semiconductor, by doping, we create a donor energy level, and this donor energy level is so close to the conduction bands such that even at room temperature the electrons jump from the donor energy level to the conduction band, and we have lots of free electrons in the conduction band, which is responsible for the current flow. Similarly, we can have extrinsic p-type material if we dope silicon with group 3 type atoms such as boron or aluminum. So note that boron and aluminum have only 3 electrons in the outer shell, and these 3 electrons will be paired up with 4 adjacent silicon atoms, but there will be one bond which will be left unsatisfied, and that can be considered that there is an absence of electron there, and that can be considered as a hole, right? And if we look into the valence band diagram view of the p-type extrinsic semiconductor, it will look something like this. So in this case, what will happen is that if when we dope semiconductor with acceptor impurities, then an acceptor energy level is created very close to the valence band, and as such the electrons can jump very easily from the valence band to this acceptor energy level, and a vacancy will be created in the valence band, which can be considered as considered as holes, right? So by doping semiconductor with either p type with the donor atom or acceptor atom, we can have extra electrons in the valence band or extra hole in the in the valence band, and extra electron in the conduction band, right? So now what this shows that the properties of semiconductor material can be tailored or can be adjusted as per our requirement, right? So by doping, we can have more or less number of carriers which will be responsible for current transport, and therefore we can actually change the conductivity of the semiconductor material by doing some changes in the material or semiconductor material, right? And this is one of the major reason why semiconductors are widely used in devices or in transistors, because in the transistors the properties of the semiconductor material can be changed much easily or can be adjusted as per our requirement. Now let us look into the carrier transport mechanism in a semiconductor. So in a semiconductor, there are two types of carrier transport or the movement of carriers. The first one is the drift, and drift is due to the electric field, right? So we apply electric field, electrons or holes move from one region to the other. That is known as drift. Okay, and the other is due to diffusion, and that occurs due to concentration gradient, meaning that if the electron concentration is high in some region, then on its own it will move towards a region where the concentration is low, right? Because of concentration gradient, there is a carrier transport, and this is mechanism is known as diffusion, right? Now both these mechanism occur in or exist in a semiconductor material, and let us understand that on what factors this drift and diffusion current transport will depend on, right? So the factors impacting the drift current is obviously, the first thing is the electric field, right? Why? Because the drift is because of the electric field. When there is an electric field applied in a semiconductor, then the electrons and holes move, right? Depending on the direction of the electric field, right? So the most important thing that impacts the drift current is the electric field, right? Then the second thing is the mobility, right? If the mobility is high, then the drift current will be drift current density, right? J drift is drift current density, and mu and mu p are the mobility of electrons and holes respectively. So the electrons and hole mobility, how much it is, that will decide the drift current density, and also the concentration of electrons and holes, right? So if in a semiconductor material the concentration of electron is high, right, then in that case by the same amount of electric field will have more drift current, right? Meaning that if the concentration of electrons in a semiconductor material is high, then its conductivity is high, right? Its conductivity is high, and therefore the more current will flow, right? So the drift current depends on the mobility, the concentration of electrons and holes in the material, and the electric field. Now, on what factors will the diffusion current will depend on, right? So diffusion current depends on diffusion coefficient of electrons and holes, and this diffusion coefficient is also related to mobility by Einstein equation, right? So the diffusion coefficient dn and dp for electrons and holes will decide the magnitude of drift current diffusion current density, and of course the concentration gradient of electrons and hole. Dn by dx is here denotes the concentration of electrons, or concentration gradient of electrons, and dp by dx denote the concentration gradient of holes. So the more the concentration gradient, more will be the diffusion current density. Now let us look into PN junction, right? So PN junction is the most basic feature or in any transistor such as MOSFETs and or BJT, and therefore we should understand the electrical characteristics of PN junction very well, right? Now what is a PN junction? PN junction is formed or gets formed when regions of P type, which is rich in holes, and N type, which is rich in electrons, are adjacent, right? Now if these two types of material are adjacent, for example, this is P type material where here we have lots of holes, right? And this is N type material where we have lots of electrons. If they are adjacent, what will happen? So we expect that there is because of the density gradient, holes will diffuse from P side towards N side, and electrons will diffuse from N type to the P type, right? Because there is a concentration gradient, both the carriers in both the side will diffuse towards each other, right? And when this diffusion occurs, what will happen, right? So now if in this region, right, this was P region, right, and this is N region. So in this part there were there were acceptor atoms like boron or aluminum, right? Let's assume that it is boron. So in this boron actually will get electrons from the other side, and this will become negatively ionized boron. And on the other side, let's assume that it was phosphorus, right? It had extra electrons. Those extra electrons has moved to the other side, and here we'll have the phosphorus donor positively charged ions, right? So in this region, we'll have only the ions, right? The negatively charged acceptor ions and positively charged donor ions, right? And this region will be devoid of electron and hole. Why it is devoid of electron and holes? Because the extra electron and holes have moved to the other side. For example, this was P region and it has gone to N region. The holes have moved to the to the to the uh, uh, N region, and the extra electrons that were there in this side that have moved to the P region, right? So we have here only ionized donors, positively charged ionized donors on this side, on the N side, and negatively charged acceptor ions on the other side. And this is devoid of or deficient of the carriers, and therefore this region is known as depletion region, meaning that it is depleted of all the carriers. So depletion region is formed at the junction, right? And at equilibrium, since we have a separation of positive charge and the negative charge, there will be there will be a there will be an electric field which will be created, right, at this depletion region. And at equilibrium, sufficient electric field and will be created that will oppose further diffusion of carriers. So from the P side, the carriers will go to N side, that is hole will go to the other side, and from N type electron will go to the P side. And though that kind of movement will go on until an electric field is created, and this electric field exactly balances the force or diffusion force, if we can say that there is a diffusion force which is moving the carriers from one side to other. So diffusive force and the electric field both are balancing out. When that balancing act is perfect and that is reached after some time, then an equilibrium condition is there, right? No further movement of electron hole pairs occur, and at that situation what we have is a built-in potential. There is an electric field is there, and therefore there is a potential barrier which is actually opposing the movement of electrons and holes to the other side, right? So at equilibrium, the potential barrier prohibits movement of electrons and holes to the other side, right? Now, this potential barrier can change when we apply voltage or bias to the PN junction, right? For example, suppose we apply a positive bias to the N type and negative bias or ground to the P type. So when we apply this type of bias, then P type region is at lower potential than the N type region. Then this is known as reverse biased condition, right? So note that P is rich in holes, and that region is connected to lower potential. If that is the situation, we say that the PN junction is reverse biased. And if the PN junction is reverse biased, then the potential barrier that was there earlier at equilibrium, that becomes wider, and the potential barrier at the junction further increases, right? And therefore in this condition no current flows, right? The potential barrier was already prohibiting electrons and holes to go from one side to other. Now when we apply this kind of bias, this potential barrier further increases, and therefore in this condition only very negligible current will flow, right? But in this situation, if we apply, say we have voltage source also, right? And because of that, the bias between P and N region, that is changing, right? So if we do that, the change in reverse bias lead to change in the depletion charge in the depletion region. So there are charges. We saw that there will be negative uh, acceptor ions and positive donor ions in this region. When we apply an AC signal, or if we are varying the voltage, this VR, then what is happening is that this charge will increase and decrease periodically, right? And we can consider that we can define a junction capacitance, or we can associate a junction capacitance with this junction or this depletion region. And how can we define this junction capacitance? We can define this junction capacitance as delta Q by delta VR, meaning that if we are making a small change in voltage from VR to say delta VR plus delta VR, right? If we are making small change, then how much extra charge is there, delta Q? Initially it was Q, and after we changed the voltage from VR to VR plus delta VR, the charge will change by delta Q in the depletion region. So we define the junction capacitance as delta Q by delta VR. Note that definition of capacitance is C is equal to Q by V. But in this case, we are defining junction capacitance as incremental capacitance, in which we are saying that then Cj is equal to delta Q by delta VR. Now the situation will differ if we apply bias in opposite direction, meaning that if we apply bias such that p-type region is at higher potential compared to n-type region, then we say that the p-n junction is forward bias. When this happens, then the potential barrier at the junction reduces from what it was at equilibrium, and this allows the carriers to move easily from the one side to the other. So when we change the polarity of the bias to the PN junction, then the current is expected to increase if it is forward biased, right? So in this case, there will be significantly higher current than the reverse bias, right? So so in summary, PN junction behaves asymmetrically to the polarity of the applied bias, meaning that if we change the polarity, like from plus minus to minus plus, then if in this case plus minus is there, plus is to terminal, or positive terminal is to P, then it is forward bias, high current flows, right? If it is negative, or negative bias is applied to P, then the it is a reverse bias situation, and very less current flow, or insignificant or negligible current flows in the PN junction, and therefore PN junction is an asymmetrical device. It allows current to flow easily in one direction but not in the other direction. So this is a major difference between a PN junction and a resistor, or a metal. A metal will allow current to flow easily in both the directions. However, PN junction allows it to flow easily in one direction but not in the other direction, and this property of PN junction is very much critical in realizing transistors such as MOSFETs and JFET and BJTs and so on, right? So therefore PN junction is a basic element of semiconductor devices. So if we want to look deeper into these topics, you can look into these two references. So just to summarize what we have looked into in this lecture, we looked into semiconductors, extrinsic semiconductors, and then we looked into carrier transport, types of carrier transport, and then we looked into PN junction and defined the junction capacitance, and why does a PN junction is an asymmetric device, and it allows current to flow easily in one direction and but not in the other direction. So that's it for this lecture. Thank you very much.